Hi, I'm Michio Okumura. I'm a professor of chemical physics here at Caltech. Welcome to sunny California, sunny Pasadena. I'm standing in front of the Linde Laboratory for Environmental Science. This building, which was originally built as a solar observatory by one of Caltech's founders, George Ellery Hale, has now been renovated and houses Caltech's Department of Environmental Science and Engineering. In this lab are, in fact, many chemistry students who work on problems in environmental chemistry, air pollution, and climate science. My own group has two laboratories here. I am interested in using the techniques of chemical physics, optical physics, and kinetics and reaction dynamics, and trying to understand problems that are relevant to the atmosphere. So what we'll do now is go downstairs to the sub-basement where two of my laboratories that use state-of-the-art laser methods are housed, and where we study problems both first looking at the reactions that lead to smog, and second to applications that are useful for satellite measurements of carbon dioxide in the atmosphere. We're now in the laboratory, the sub-basement of the Linde Robinson Laboratory, and in this sub-basement there are several groups doing experiments on in atmospheric chemistry, in particular, from field research to laboratory work. Two of my own laboratories are down here, and so we'll go take a look at one on air pollution chemistry and another involved in climate science spectroscopy. Right. So our research involves the use and development of state-of-the-art methods in physical chemistry, in particular modern high-resolution, high-sensitivity laser methods for the study of atmospheric gases and aerosols. Part of our goal is to try to understand the mechanisms and reactions that are important for the formation of photochemical smog, as well as related chemistry in planets such as Mars, Jupiter, Saturn. We also do experiments where we try to understand the spectroscopic properties of molecules that are important in our understanding of Earth's climate. This particular lab is focused on a fundamental problem in atmospheric chemistry, which is the fate of organic molecules which are released either by man or biologically, and how those organics degrade and form toxic pollutants or aerosols and contribute to the degradation of air quality. Much of our research, in fact, is then used in models that the EPA and EPA and CARB use in order to develop regulations for emissions of things like auto exhaust, nitrogen oxides, and so on. And so our research has a very fundamental importance. But we're also, as chemists, interested in reaction mechanisms. And so we are particularly interested in detecting trace amounts of reactive free radical intermediates and trying to understand in as much detail as possible their spectroscopy and their reactions and dynamics. This particular experiment uses laser chemistry to initiate and form some of these radicals that we're interested in, and then we use a technique called cavity ring down spectroscopy, one of a number of methods that use modern techniques such as optical cavities to try to maximize our sensitivity for these highly reactive trace species, and we try to detect them uniquely and then follow their reactions in real time. And over here we can see part of the laser system used to generate light in the infrared in this particular case, and then over here we have a reaction cell, our reactor, where we actually do the chemistry. We've studied a number of molecules such as isoprene, which is an organic molecule which is released primarily by deciduous trees, so of biological origin, but the isoprene photochemistry and its degradations are a major contribution to aerosols, to aerosol and air quality degradation, especially over areas that have high plant populations. Now what I want to do is have my student Elizabeth Lunny, who will be graduating in a couple months, show you another laboratory down here where we are using similar high sensitivity, state-of-the-art laser methods to look at problems in climate science, in particular in collaboration with the NASA Jet Propulsion Laboratory.
Hi, my name is Elizabeth Lunny, and I'm a grad student in the Okumura group. I'm working here in the quiet room where we're doing high-resolution spectroscopy in support of OCO2. So OCO2 is a NASA satellite measuring the global sources and sinks of carbon dioxide. So we work with a big team of scientists and collaborate with a lot of people at JPL and NIST, the National Institute of Standards and Technology. So the goal of the OCO2 mission is to measure the global sources and sinks of carbon dioxide. And there's a lot of satellites measuring total carbon dioxide, but here we're trying to see where CO2 is appearing and disappearing with very high spatial and temporal resolution. So we're trying to make maps of the Earth that look like this, where we see this appearance and disappearance of CO2 on very small spatial scales like cities. The overall goal of the mission is to measure the concentration of CO2 with 1 part per million accuracy. And the overall concentration is around 400 parts per million, so that means we want to know, is there 399 or 400, which is trying to measure very, very small changes from a satellite in space. So that 0.25 accuracy goal places very stringent requirements on our understanding of the spectral parameters. Now the mission works by having 3 grading spectrometers mounted on the satellite here, which looks at reflected sunlight off the Earth's surface. So any carbon dioxide in the air will absorb at certain wavelengths, and we can spectrally detect the concentration of CO2 in a air column. So the satellite has 3 bands that it measures, 2 carbon dioxide bands and 1 oxygen band. The use of the oxygen band is to determine the solar path length if your light is bouncing off aerosols or clouds or anything like that, due to the uniform, well-known concentration of oxygen throughout the atmosphere. So any error in oxygen spectroscopy propagates through to the final retrieved column density of CO2. And for that reason, we have to know all of the oxygen spectral parameters to less than 0.1% absolute accuracy, which is a very stringent goal. And that's really what we're working on in this room, is trying to measure those spectral parameters. Currently, the largest spectroscopic uncertainties for OCO2 come from high pressure effects in the oxygen A band. So we're using photoacoustic spectroscopy, which has a very large dynamic range and no baseline effects, so that we can observe where those high pressure effects are coming into play without saturating our spectra. We have our photoacoustic cell inside this chamber here, which is set up for temperature control and acoustic isolation. We have oxygen in there, and we can control the temperature really well, so we can measure over relevant temperatures to the atmosphere. I've been working on this project for about 6 years, but I'm done now. I'm about to graduate. And it's been really fun to be able to work with really state-of-the-art equipment, cutting-edge things, and doing this spectroscopy to accuracies that no one has done before, and seeing information in our data that we also see in the satellite data, but no one else has seen in lab before, so that we can inform the models for the spectroscopic retrievals for OCO2, which is also a very important mission. Obviously, trying to map CO2 has a lot of societal impacts. So I'm sorry you couldn't come here today to see all this equipment in person, but I hope that you will come in the fall and get to see all of the really exciting science that we're doing here.